When we're considering the rates of concentration, either depletion or increasing, as reactants are consumed and products are created, it's important that we know how to relate them together. Previously, when we've looked at our reaction A goes to B, we saw that the rate was the negative change in A over time, which was the same thing as the positive change in B over time. And that worked. Wow, that's a terrible arrow. That worked because the coefficients of A and B were both 1. But what happens when we take a reaction that has new coefficients, or coefficients that aren't 1? Well, we know that our concentration of reactant is going to go down, so we're going to need a negative there. And we know our concentration of product is going to go up. And in this example, we see for every 2 molecules of ozone, we get 3 molecules of oxygen gas, dioxygen out. And so if we want to standardize these, well, we know it's a 2 to 3 ratio that's coming out, right? We lose 2 and we gain 3. But in order to standardize that, it might be easier to instead apply those coefficients as fractions. For this particular reaction, we'll see that if we take half the rate at which O3 is depleted over time, we would see that that's 1/3 the rate at which dioxygen is appearing. We know this because it's a 2 to 3 ratio happening here. If we want to standardize these to make them a 1-to-1 comparison, well, we just need to divide by our coefficients. Since we know it's 2 molecules of ozone that are being depleted, if we want to look at the rate at which 1 molecule of ozone is depleted, that would be half that, right? And because each reaction takes 2 molecules. So if we want to see the reaction for 1 molecule, we just need half that rate, because we have twice as much data. And then the same thing for the reaction, the product being produced, we're producing 3 molecules every time we do this reaction. So if you want to see the rate of 1 molecule being produced, that's simply 1/3 the total change. And so we can see here that the rates of this reaction would simply be the inverse of the coefficient multiplied by our normal rates. And we can kind of generalize this to the following. If we now have several different components in our reaction, the rate of this reaction will always be negative for our reactants. So we would say -1 over A times the concentration of A over time, which is equal to the same thing for B, delta B over time, which would be +1 over C, delta C over time. And let's see if we can fit this in here. 1 over D times concentration of D over time. So all of these are related to each other through stoichiometry. For whatever your coefficients may be, however many reactants or products you have, you can relate the rates of each to each other by looking at their stoichiometric ratios to each other. Remember that all reactants should be negative because those concentrations are going down. So in order to standardize the rate to make it positive, we're going to have negative in our formula here. And then our products, of course, will be positive. And so, with this information, we can see how to relate the rates of concentration, of change of concentration of one component of our reaction to another. And so this is very useful because sometimes it's very difficult to measure a particular product, but it may be very easy to measure the change of concentration of a reactant. And so we can get information then about how the product is being formed in the same way. And so, in our next video, we'll go ahead and look at instantaneous rates of reaction and evaluate things on a much smaller time scale than the entire course of the reaction.